In this lesson, I'm going to talk about another gas law, which is the ideal gas law or the ideal gas equation. So just as review, when we were working with our gas laws before, we were actually changing 4 different variables. We were working with pressure, volume, temperature, and number of moles. Here are some of the relationships that we looked at. In Boyle's law, volume is inversely proportional to pressure. In Charles's law, volume is directly proportional to temperature. And in Avogadro's law, volume is directly proportional to number of moles. So if we take these 3 laws and combine them together, what we find is that volume is proportional to number of moles times temperature all over pressure. Now, proportional does not mean equal, and in order to create that equal sign and actually create an equation, we need a constant. And so that's accomplished with R, which is our gas constant, which we'll look at in just 1 second. If we rearrange this, what we end up with is our ideal gas equation, which is pressure times volume equals number of moles times R times T. Now, this is called the ideal gas equation because we're assuming that gases are acting ideally. So what exactly does that mean? The first thing is that we're assuming that the molecules of that gas do not interact with one another. The second assumption that we're making is that the combined volume of the molecules is going to be much smaller than the volume that the gas itself occupies, to the point at which we ignore it. The very last lesson of this unit, we will actually compare ideal gases with real gases, learning in fact that these 2 statements are not true and that will impact our calculations. But for right now, we're going to ignore that fact and assume that gases act ideally. Now, I had talked about the R, which is your gas constant. The value that we're going to use for your R is 0.08206. Notice the units. The units for your R are liters, atmospheres over moles, Kelvin. Liters, therefore, have to be the units for volume. Atmospheres are the unit for pressure. Moles are the units for number of moles. And temperature units are Kelvin. So this gas constant actually dictates what your units for your measurements must be. When we were working with stoichiometry, one assumption that we made was that if we have a gas at STP, then 1 mole of that gas will have a volume of 22.4 liters. So let's actually use the ideal gas equation in order to understand where that number came from. So if we're assuming we have 1 mole of our substance, we have our R, which is our constant. The temperature, which we had stated for standard temperature and pressure, is 0 degrees Celsius, which is 273 Kelvin, and our pressure is 1 atmosphere. What we end up getting mathematically is 22.4 liters. So that's where that value came from. Now you can actually understand where it came from. Now, if you notice, the molar volume for an ideal gas, 1 mole of an ideal gas, is 22.4 liters. Now, if you look at these other gases, their molar volumes are not exactly 22.4, and the reason why is that these gases are not acting ideally. We had just talked about that in the previous slide, the fact that gases actually are slightly attracted to one another, and the fact that they do take up volume. So for right now, assume whenever you see 22.4, we're assuming that the gas is acting ideally and that we're ignoring the fact that gases that actually exist do not act ideally. We call them real gases. So let's actually look at an example. In this example, it says that a flashbulb of volume 2.6 centimeters cubed contains oxygen gas at a pressure of 2.3 atmospheres and a temperature of 26 degrees Celsius. It asks you how many moles of oxygen does the flashbulb contain. So we're going to be using our formula PV equals nRT. We're solving for N, but we've got to figure out the other variables. R is going to be our constant, and that will help us in determining what the units for our other measurements need to be. So volume must be in liters, pressure must be in atmospheres, number of moles is in moles, and then temperature is in Kelvin. So I've got some converting to do. The first thing that I need to do is convert volume from milliliters, because remember centimeters cubed is synonymous to milliliters. I need to convert milliliters to liters. And I do that by putting 1,000 milliliters in the denominator and 1 liter up top, and so I end up getting 0.0026 liters. The next conversion that I need to do, well, for 2.3 atmospheres, I don't need to perform a conversion because I'm already in atmospheres, which is the units that I want for pressure. Next, for temperature, I'm in degrees Celsius, but I want to be in Kelvin. So I have to take 26 degrees Celsius and add 273 to that. And what I end up getting is 299 Kelvin. So what I'm going to do is I take my pressure, which is 2.3 atmospheres, and I multiply that by my volume in liters, and I set that equal to my number of moles, N, times my R, times my T. Notice I've included all of these units here just for me to be able to check to make sure, yes, my liters are the same on either side, so they will cancel, atmospheres are the same, and Kelvin will cancel. So in the end, my final units will be moles. So I get 2.437 times 10 to the negative 4th moles. Keep in mind that I only want 2 significant figures, so my final answer will be 2.4 times 10 to the negative 4th moles. Keep in mind for this problem that I'm assuming that my gas is acting ideally, and therefore I can use my ideal gas equation. Now, I want you to solve B and C. So pause this video. The next concept that I'm going to talk about is gas mixtures and partial pressures. Now, Dalton noted that the total pressure of a mixture of gases equals the sum of the pressures that each would exert if it were present alone. Those pressures that each exert by themselves, those are called partial pressures. And so what he created was this law of partial pressures in which the total pressure equals the sum of each of the partial pressures. The fact that he viewed this is a result of the fact that gases, as we had noted before, when they're in mixtures, they still act independently of one another. And so that's what allowed Dalton's law of partial pressures to exist, because they're simply the pressure is simply the sum of all of their pressures together. So if we take Dalton's law of partial pressures and we use it in conjunction with the ideal gas equation, what we can actually discover is that the pressure of the first gas that we're noting equals its number of moles times R times T all over V. Same thing with the second gas. Notice that R, T, and V remain constant, and so what I can actually do if I'm going to sum these partial pressures is I can just add up the number of moles and then multiply it by R, T all over V. So this is just one manipulation that I can use in order to calculate pressure if I know the number of moles of each gas that are involved. The next concept that I'm going to talk about is mole fractions, and I'm going to talk about mole fractions in the context of partial pressures, which we've already talked about. So if you look right here, the mole fraction that you see is the number of moles of the gas that you are concerned with divided by the total number of moles. And so the mole fraction, if you multiply it by the total pressure, that will give you the partial pressure of the gas that you're concerned with. Another way of representing mole fraction instead of N1 all over N total is just with that X1. That represents the mole fraction for that first gas. So let's look at an example problem. This example asks you what pressure in atmospheres is exerted by a mixture of 2 grams of hydrogen and 8 grams of nitrogen at 273 Kelvin in a 10-liter vessel. So the first thing that I need to do is to determine how many moles of each substance I have. So I'm going to convert this into moles by using the molar mass of hydrogen, and that gives me 0.992 moles. I now need to find the number of moles of nitrogen, and I complete that, and I find that the total number of moles is 0.2855 moles. Now, if I want to know the total number of moles, all I have to do is add them together. And now I'm going to find the pressure that the entire mixture exerts. Therefore, I can just use the total number of moles, as I noted in the previous slide. So I'm going to use my ideal gas equation. My pressure is what I'm solving for. I know my volume because that's given to me. I now know my number of moles because that's just the total number of moles, and I know my temperature. And so I plug in everything, and then I can solve for my pressure, which is 2.86 atmospheres. Notice I can also take each of these individual number of moles and plug them in for N in the ideal gas equation, solve for 2 separate pressures, and then simply add them together. So this is extremely convenient, and we might take this for granted, but the only reason why we're able to do this, either adding up the number of moles or adding up the pressures, is because gases don't interact with one another, and therefore their pressures simply sum together. The last concept that I'm going to talk about is the laboratory technique of collecting gases over water. Now, the purpose of collecting gases over water is it's actually a stoichiometry technique that allows us to determine the volume and the pressure that a gas exerts in order to determine how much, either moles or grams, that are being produced. So specifically in this example, KClO3 is being decomposed to produce oxygen. Now, you might think collecting oxygen is really hard. How can I determine the pressure it exerts, and how can I determine the volume that oxygen occupies? Well, you do that by collecting the gas over water. So specifically, you have a container that has water in it, and so the amount of air that you see up top, that is how much oxygen has displaced the water. So you can actually measure the volume of oxygen that's produced. And then through a little bit of manipulation that this describes, by making sure that the levels of water are equal, you can actually determine the pressure of that oxygen within the container. Now, the total pressure within that container is equal to the atmospheric pressure, but the important thing for you to know is that that total pressure is not just the pressure of the gas in question, oxygen in this case. The pressure that water vapor exerts, because you are right above water, that also influences it. So the total pressure within that container actually equals the pressure of the gas plus the pressure of water. And so to determine the pressure that the gas exerts, you simply have to take the total pressure, which is equal to the atmospheric pressure, and subtract the pressure of water. So let's look at an example. So in this example problem, it tells you that you have 90 milliliters of hydrogen gas that's been collected over water. The temperature is 25 degrees Celsius and the atmospheric pressure is 755 millimeters of mercury. It's asking how many grams of calcium hydride decompose if the vapor pressure of the water is 23.8 millimeters of mercury. So here's the reaction that's occurring. What you've measured is the volume of hydrogen, and so what I'm going to have to calculate is how many moles of hydrogen were produced, and from that, with stoichiometry, I can actually calculate how many grams of calcium hydride were required to make that much hydrogen. So if I get started, I know that the pressure that hydrogen gas exerts equals the total pressure, which is the atmospheric pressure, minus the pressure that water exerts. So the total pressure is the 755 millimeters of mercury minus the vapor pressure of water, which is 23.8 millimeters of mercury. So I know that the total pressure that hydrogen exerts is therefore 731.2 millimeters of mercury. There's the first step. What I need to do now, since I'm going to be using my R, I need to convert millimeters of mercury into atmospheres, and I can do that quite simply, and I get 0.962 atmospheres. The next thing that I'm going to do is I'm going to plug in all of my values into my ideal gas equation. So I know that my pressure is 0.962 atmospheres. I know my volume is 0.0900 liters. I converted milliliters to liters. I don't know the number of moles of hydrogen gas. I know my R, and I converted the temperature from 25 degrees Celsius to Kelvin, so it's 298 Kelvin. So when I solve for N, I get 0.00354 moles of hydrogen. Now it's just basic stoichiometry to determine how many grams of calcium hydride are required. So I'm going to take my moles of hydrogen gas, convert that first into moles of calcium hydride. There's a 1 to 2 relationship because notice that reaction up top is already balanced. And then I'm going to convert moles of calcium hydride into grams using the molar mass of calcium hydride, and I end up getting 0.0745 grams of calcium hydride. And that's my final answer. So notice I'm now being able to incorporate this concept of collecting a gas over water, ideal gas equation, and stoichiometry.